Hi everyone. Thank you. I'm Keunho Kim, a postdoctoral researcher at University of Cincinnati. I'm working with Matthew Baylis. And first of all, thank you for the organizers of the conference and for giving me the opportunity to present our results. Today, I'm going to talk about our results on cluster environmental quenching effects based on the info time averaged analysis since Redshift 1. Where galaxies live, environment matters for their lives and death quenching, as environment is one of the two main factors to quench star formation in galaxies. Typically, star formation in galaxies in denser regions tend to get more suppressed in star formation compared to isolated field galaxies. This figure shows, in particular on y-axis, the environmental quenching parameter from sparse to dense with stellar mass. And the color indicates the fraction of quiescent galaxies. And as shown here, at any given stellar mass, galaxies residing in dense environment have higher fraction of quiescent star formation suppression. While such environmental quenching trends are relatively well established in the local universe, there is not yet a clear picture, in particular on the cluster environmental quenching effect at higher redshift due to observational challenges for selecting clusters with accurate cluster memberships at high redshift. To better understand the quenching effects at higher redshift, we aim to study the first systematic time-averaged kinematic approach for the cluster environmental effects beyond local universe by covering a wide range of redshifts. The method we are primarily using is based on the info time resolved analysis through projected phase space diagram. The phase space diagram is the diagram where we can infer the dynamical stage of galaxies based on the peculiar velocity and the cluster-centric radius. For example, if this galaxy in the field is infalling into the cluster's gravitational potentials, and as it or orbiting and infalling into the cluster center from infalling and orbiting and finally get virialized, we can infer its dynamical stages, either 1, 2, or 3, from the base from this phase space diagram. This is well shown in the simulations here. As shown here, the red color, which is the early infalling galaxies, is well separated. The recent galaxies with blue color that are recently infalling galaxy populations in this phase space diagram. So from which we can infer when galaxies enter into clusters based on this phase space diagram. This is also shown in another simulations. And observationally, this is also well shown from in the observed sky projected phase space diagram from galaxy cluster outskirts to the cluster center. We sampled galaxies in Sunyav-Zeldovich selected clusters from SPT and ACT surveys. So here, the redshift versus cluster mass, and our sample clusters are subsamples of this black dotted SPT survey and green data points from ACT surveys. We select clusters above about 3 times 10 to the 14 solar mass uniformly at all redshifts of our interest. And from the optical follow-up, we obtain I-band luminosity. And we use galaxies only brighter than 1/3 of the characteristic luminosity for our throughout our entire redshift. And from the optical follow-up, we also obtained the spectra 4000 break feature as an age indicator. So from the accurate measurement of peculiar velocity and the cluster centric radius, our sample cluster galaxies also show very well-behaved distribution in the phase space diagram. And we class based on the location in the projected phase space diagram and adopting the same criteria based on the caustic lines, as shown here, black lines. We classify galaxies either early infall within from the field and recent infall between these two black lines, and the mixed and backsplashed population between these two lines, and the innermost early infall populations following the same criteria by Noble et al. 2013. Here is the result. First of all, each galaxies have become quenched since infall by showing a gradual age increase from field here to early infall galaxies. These colored diamonds are the bootstrapped mean values of the D4000 of each infall region. And as shown here, there is a gradual increase. And this trend is qualitatively consistent with previous studies for a small number of samples or in the local universe. Yet we are spanning a wide redshift range. And also, the D4000 distribution of each infall region shows statistically different distributions based on the KS test. This suggests that cluster environment is indeed impacting the over mean age of clustered galaxies. And based on the simple stellar population modeling, the DM4000 increase from field to early infall roughly corresponds to 2 giga-year older age in early infall galaxies compared to the field feed galaxies. And this is all shown at all redshift, or if we divide into 2 redshift, the trend is also shown the same. And a high redshift subsamples also shows the increasing trend as well. Now we also check the galaxy's luminosity dependence on this infall time based cluster environmental quenching trend. Whether we divide galaxies into faint and bright subsamples based on the characteristic luminosity. First of all, both faint and bright galaxies show the same, the increasing age trend from field to early infall. Oh, but in addition to that, we see that at fixed infall time region, bright galaxies show a larger value, mean value of DM4000, meaning the older age compared to the faint counterpart. This suggests that environmental quenching and mass quenching are separately at work throughout the dynamical settle down of cluster galaxies since infall. Lastly, we investigate the redshift dependence or the redshift evolution of this infall time-related cluster quenching effects. Here, the blue points are the low redshift subsamples, and the red points are the high redshift subsample. First of all, while the field in the field region, both low and high redshifts are subsamples are having the similar age, DM4000 values, they become different as galaxies enter into the cluster environment, in the sense that low redshift cluster galaxies are more suppressed compared to the high redshift counterparts at fixed infall time. This is still observed whether whether galaxies are on faint or bright. Just to recap, at all fixed infall time region, low redshift cluster galaxies show about 1 gigayear older age than the high redshift counterparts. As this trend is not observed in the field region, it seems to suggest more efficient quenching happening in low redshift clusters compared to high redshift clusters. Here is the summary, and one sentence takeaway is our analysis shows cluster environments do quench star formation of galaxies since infall with time averaged analysis, independent of mass quenching at all redshifts up to redshift 1. And we are, and I'm thank you, and I'm happy to take questions.